All right, so this is the last little piece here of section 4.6, and we'll be talking about one more application of algebraic fractions, which is the similar triangles. This is something that you may have seen before, like in a high school geometry class or something, but for most people it's not super fresh in their minds, so let's go ahead and talk a little bit about it. First of all, what is a similar triangle? Triangles are similar if they have the same angles. So basically, like if you look at these two triangles down here, they both have a 90-degree angle, right, a right angle. And then just visually, you can kind of see that that angle, those two angles would have the same degree measure. And these two angles up here would also have the same degree measures. So if they have all the same angles, the triangles are what we call similar. Right? Now you can make them really small or really big in terms of the lengths of the sides, but the angles themselves don't change. If you have similar triangles, the ratios of the corresponding sides are equal. And that means that I can write some proportionality statements. It says write 3 of them. Basically what that means is I can say that whatever the ratio of little a to big A is, that same ratio applies to little b over big B. Those fractions are equal, and we call that statement a proportion. I can compare the A's to the C's as well. Or I could compare the B's and the C's. So those are my 3 proportionality statements. And given enough information about a triangle, I can generally use those statements to help me figure out more information or finish solving for the various sides of a triangle. And that's what we're going to work on in a couple of examples here. All right, so first of all, in the first example, we want to know, are the triangles similar? And it says to explain. So in terms of being similar, I'm going to start by noticing that that little square in the corner means that those are right angles or 90-degree angles. So yes, they both have a 90-degree angle. And then I have to show that the other angles are equal as well. To do that, I'm just going to use the fact that the sum of the angles in a triangle is 180 degrees. So for example, if I were to take this little triangle right here, I know altogether I have 180 degrees. I have a 90-degree angle already accounted for. And I have a 53-degree angle already accounted for. So that tells me that the remaining angle would have to be 37 degrees. And again, I just got that as 180 minus the 90 minus the 53. I'm sure you can already see it coming here since I gave you the 37-degree angle, but let's just work it through real quick. To figure out the missing one, I would go ahead and say, I know altogether the angles are 180 degrees. I already have a 90. I already have a 37. So of course that leaves 53 for the third one. So they both have 37-degree angles. And they both have 53-degree angles as well. In actual fact, as long as you got 2 angles the same, you kind of get the third one for free because of that sum of 180-degree thing. All right, so check, yep, triangles are similar, and we've done our explanation. I'm now asked to fill in the missing sides. So I'm going to go ahead and label some of the sides here. In the little triangle, I actually know them all. So I'm going to call those small letter A, small letter B, and small letter C. And then the corresponding side for little a would be this vertical side here. We don't know the value of that yet. For little b, the corresponding side capital B, and then little c has this corresponding side capital C, which we do know the value is 15. Now, in this particular case, I gave you fairly easy numbers to deal with, so we can probably just mentally predict the answers. I want to go ahead and do that, but then I'm also going to run through the actual math so we can see how it works in the cases that aren't quite so obvious. So in this case, I'm going to notice here that with the C's, I know both C's, and it's pretty clear that the large triangle is just 3 times as big as the small triangle. So going with that, I can kind of predict that that A is going to be 3 times as big. That'll be 9. And B will also be 3 times as big. That'll be 12. Okay. Now, the multiplier is not always that obvious. So even though we already know the answers, let me run through the mathematical process with you just for practice, and then we'll look at some more complicated problems on the next page. All right, I'm going to go for the A's first. So I would start by saying little a over capital A. And then you always want your second fraction here to be a value that you know both the little and big values for. So in this case, I'm going to go with the 5 over 15 for the C's. Using our technique from this recent chapter, I might say that with, that little a is 3. I should have filled that in. Say there's too many variables here. There we go. So little a is 3 compared to capital A, and little c is 5, capital C is 15. There we go. All right, now, using the techniques from the chapter that we were just working with, we can go ahead and we can get rid of the denominators if we just multiply by the common denominator, 15a, right, clearing fractions here. And over here, the a's will divide out. 15 times 3 is 45. Over there, the 15s will divide out. I get 5a. And then dividing both sides by 5, I do get a equals 9, which of course is exactly what we expected since we knew the multiplier of 3. But that would be using the proportion to figure that out. Let's run through the same thing with the b's real quick. For the b's, little b is 4, capital B is unknown. I'll set that equal to little c is 5 over capital C is 15. And then same deal. I'd like to get rid of the fractions, so I'm going to multiply by the common denominator, 15b. Left side, 15 times 4 is 60. And the right side, I get 5 times b. Divide both sides by 5. And 60 divided by 5 is 12 for b. Again, not at all unexpected. That's exactly what we thought it was going to be. All right, let's take a look at another example where the numbers perhaps are not quite so obvious. In example 2, I've given you 2 isosceles triangles, and I'm told that they're similar, so I don't have to prove that. The problem gives me that. And I'd like to find the value of this side, this unknown x. First of all, isosceles. Probably a word, again, you've seen it before, but if you don't remember what it means that 2 sides are the same. So essentially, in this problem, it means that if the left side is 6.3, I can automatically fill in the right side, also 6.3. And the 8.82, again, would have the same value for the left side. So I've got my two equal sides in each triangle. All right, let's go ahead and do some labeling. This doesn't happen to be a right triangle, but I can still pick out an A, a B, and a C. So I'm going to go with A, B, and C. And then enlarge one, corresponding sides capital A, capital B, and capital C. All right, I'm ready to set up my proportion. And I'm going to notice that my unknown here is going to be one of the B's. So I definitely want to include the B's. And I can go with either the A's or the C's. They're actually identical in this case. So I'm going to set this up as A over A equals B over B. That would be 6.3 over 8.82. Equals 4 over x. All right, I've got my proportions set up. So I'm going to clear the fractions. I'm going to multiply both sides by the common denominator, which would be 8.82x. And on the left side, I can divide out the 8.82's. So 6.3x. On the right side, I can divide out the x's. So I've got 4 times 8.82. 35.28. If I divide both sides by the 6.3, I have 5.6. So the bottom of this triangle would have a length of 5.6. All right, we've got one more problem here. There's an application or word problem here. Jim wants to figure out the height of a tree in his yard, but doesn't have a way to reach the top to actually measure it. Standing in his backyard, he has his wife measure the length of his shadow, which is 10.5 feet, as well as the tree's shadow, which is 73.5 feet. If Jim is 6 feet tall, how tall is the tree? Although it may not jump out at you right away, this is actually a similar triangles problem. Let's start with Jim himself. So here's Jim. He's 6 feet tall. And his shadow here, so this is the shadow he's casting, is 10.5 feet. Now, I'm going to draw a dotted line here. It's not a true, physical thing, but it does complete a triangle, so I can start to think about similar triangles. Let's do the same thing with the tree. Tree obviously much longer, shadow much taller. So let's see, we don't know the height of the tree. That's our unknown x that we're trying to find out. But we were able to measure the shadow here along the ground, right? The shadow is 73.5 feet. And again, just going to kind of create the triangle by drawing that in as a dotted line. All right, if these are similar triangles, I'm going to be able to set up my proportion and solve for x. But I probably should convince myself that they're truly similar triangles. First of all, I'm going to assume that Jim is standing up straight and that the tree is standing up straight. So those are right angles. It doesn't say so in the problem, but those are pretty reasonable assumptions. That I've got a 90-degree angle between the tree and the ground, and also between Jim and the ground. Now I need at least one more angle to make the argument that these are similar triangles. And I'm going to actually ask us to focus on these angles down here. I claim that those two angles have to be the same as long as these measurements were made at the same time of day. Here's the reason. What causes a shadow? Well, what causes a shadow is blocking the sun's rays. So if I continued on up here, I would have the sun here, right? The sunbeams shining down, and they were blocked in here, causing the shadow. Now the same thing would happen here with the tree. Right up here, there'd be a sun somewhere. And again, the tree blocked part of the sun's rays, causing that shadow. As long as the measurements are made at the same time of day, the angle of the sun in the sky has to be the same. So I'm actually going to use kind of a physics or a meteorology argument and say those angles are the same, not so much mathematically reasoning, but just reasoning that the sun would be at the same angle in the sky. All bets are off if they measure the shadows 2 hours apart or something, but as long as they measure them at basically the same time, we're good to go. All right, so let's set up our proportion. In this case, I don't have that third side, and I don't really need it. I can just go ahead and say 6 over x equals 10.5 over 73.5. I didn't label the letters here, but I could have, right? I could have called this, say, A, and capital A, and B, and capital B. So I just said little a over capital A equals little b over capital B. All right, from there, we're going to use our usual, let's clear the fractions. I'm going to multiply both sides by the common denominator, 73.5x. And on the left here, the x's are going to cancel out. So I have 73.5 times 6. It's 441. And on this side, I can divide out the 73.5s. So I've got 10.5x. If I divide both sides by 10.5, I have 42. So this tree is 42 feet tall. All right, that brings us to the end of section 4.6. You should be good to go to finish up the homework.